again, did we ever talk about this or no? We never talked about the graph where the line plateaued? Okay, so let's talk about it. So in order to determine how fast a particular enzyme reacts, because different enzymes have different rates of reaction depending on how well they grab onto the substrate. Enzymes that don't grab onto the substrate very well have a slow reaction rate. And on the flip side of that, enzymes that grab onto the substrate really well have a really fast reaction rate. So we can't use a microscope and zoom in and actually see the enzyme grabbing onto the substrate. Number one, it happens way too fast for us to see. And number two, it happens at a much smaller scale than we can see with a light microscope. So we can't actually observe the enzyme and the active site in the substrate. But what we can do is we can measure the rate of the reaction by ways that you'll learn eventually. For now, though, just understand that we have ways to measure the rate of the reaction. Like, let's say that as the reaction progresses, the solution gets darker and darker. That's one way that we can measure reaction rates, is by looking at how quickly a solution gets dark, which indicates that the reaction is proceeding. Anyway, let's do 7 experiments. In experiment number 1, we have some concentration of enzyme. The enzyme concentration in all of these experiments never changes. The only thing we're changing in each experiment is the concentration of substrates. So in experiment number 1, and on my y-axis, I'm going to have rate, how quickly the reaction happens. And remember, when I'm looking at the rate of a reaction, do I always look at the rate at the beginning, the middle, or the end of the reaction? If I want to know how fast a reaction occurs.
Middle.
Not the middle,
End.
not the end.
Beginning and end?
Why the beginning?
No, because like, I guess, however long it takes to get the first one is the one.
No, I mean, that's not
After time,
quite.
it's gonna be less substrates to break down.
Okay, so at the beginning is when the concentration of substrates is always at the highest concentration, which means that that is going to be the point in time where the collision between active site and substrate is most likely. More substrates equals more collisions equals more reactions. So the chemical reaction that we're measuring, we're always going to measure what's called the initial velocity. The initial velocity just means the very beginning rate. The very beginning rate, because, keep it going, come on. Let's do like a sneezing jingle bells. Choo, choo, choo.
Like the kitty.
Just don't sneeze and fart at the same time, because then that'll ruin everything. I'm just saying, make sure that doesn't happen. That would be awkward. Okay. Anyway. So, experiment number 1, we see that at this substrate concentration, there's this rate. Okay, no
That was
big deal.
cool.
That really, huh?
You made it go with your finger.
Huh?
Did I?
I'm pretty sure.
No, I'm pretty sure I did.
Okay. I think.
Anyway, this by itself doesn't tell us anything. This doesn't mean anything. So we need to conduct a second experiment. And this time, in our second experiment, we're going to increase the substrate concentration and see how that affects the rate. You tell me, if I increase the substrate concentration in experiment number 2, is the initial rate going to be faster or slower?
Fast.
Probably faster, because there's more substrates to react with the active site. Show it over here, guys. Experiment number 2, that's exactly what we see. Experiment number 3, we're going to increase the substrate concentration even more. And we're going to see that the initial rate is even faster. We do it again for 4, 5, 6, and 7. All of those are different experiments. Now notice here that after we hit a certain substrate concentration, it doesn't matter what we do, the rate never gets any faster. Don't be fooled and think that this means that the rate is 0. The rate is definitely not 0. It's just that the rate doesn't increase as we increase the substrate past a certain point. Why is that? Jack?
Okay, that's true because the enzymes are working as fast as they can.
Good. They're working as fast as they can, We call that two different things. We can call that Vmax, which stands for maximum velocity. We can also call this point saturation. Saturation simply means that as soon as the active site spits out the product, immediately another substrate comes in and spits out the product. And then immediately another substrate comes in and it spits out the product. In other words, the saturation point for an enzyme is when the active site is working as fast as it can and it can't possibly churn out any more products. So the analogy for that is if I give you a pile of 20 toothpicks, let me do another slide. I give you a pile of 20 toothpicks, and then 200 toothpicks, and then 2,000 toothpicks, and then
200,000.
20,000 toothpicks. Here's the idea. The objective is to break as many toothpicks as you can in 1 minute. And the way that you do it is you have to, in order to simulate randomness, you have to close your eyes, reach into the toothpick pile, pick up one toothpick and snap it. Drop it. Pick up a toothpick, snap it, drop it. Pick up a toothpick, snap it, drop it. What happens, by the way, if you pick up an already snapped toothpick? Are you going to be able to break it down even more?
Not as easily.
No. No. If anything, right, if the reaction is reversible, I would be able to reform that toothpick. But the point that I'm trying to make is that as the substrate concentration decreases, the reaction rate decreases because number one, there are less substrates, but then also number two, the products are kind of competing for that active site. Does that make sense? So let's say in this scenario, in 60 seconds, you snapped 15 toothpicks.
Ooh, I'm gonna do it.
No, I don't want to do that. You snap 20 toothpicks. In this scenario, you snap 35 toothpicks. Right, let's say in this scenario, you were able to snap them all before that 1 minute came up. In this scenario, you can only snap 35. In this scenario, you could also only snap 35. In this scenario, you could also only snap 35 before the time came up. In other words, your fingers have reached Vmax. It doesn't matter how many toothpicks I throw in front of you. If I give you 2,000 toothpicks versus 2 million toothpicks, your fingers can only work so fast and snap so many toothpicks before the time runs up. That's exactly the same concept that's happening right here. At a certain point, enzymes can't work any faster, and giving them more substrate isn't going to magically start making them work any faster. Just like giving you a pile of 2 million toothpicks versus 200,000, you're not going to be able to snap any toothpicks any faster in those two piles. Yeah? That's called Vmax. Let's call this red line our baseline. Our baseline is just really like our frame of reference. And by the way, you have this graph on the back of your sheets that look like this. It's the lactase sheets. On the back, you've got these graphs. Yes, Doug?
So do you want to send in our parent information form?
Yes, in a second.
Okay.
Okay. If you introduce a competitive, let's do the experiment again, except this time we're going to introduce a competitive inhibitor. So the competitive inhibitor on this graph is this line that's in the middle of those three lines. So for the competitive inhibitor, we have the same substrate concentration as our baseline, except now there are competitive inhibitors present. And what we see is that the initial rate is slower at that same substrate concentration. Why is the initial rate slower in the presence of a competitive inhibitor?
Because it has to do more. There's the low probability of grabbing a substrate.
Good. The probability of grabbing an actual substrate goes down because now there's also a chance that it could grab onto a competitive inhibitor. And if it grabs onto a competitive inhibitor instead of a substrate, no chemical reaction happens. So it's sort of like in that toothpick analogy, now in this pile, I'm gonna throw in some paper clips. And whenever you close your eyes and reach in, if you pick up a paper clip instead, you have to try to break it, you can't break it, and then you drop it again, and then you reach back in the pile. So in other words, because you took time trying to break this, the reaction rate slowed down, so maybe in the presence of a competitive inhibitor, you were only able to break 12 toothpicks in a minute because you wasted so much time picking up those paper clips by accident. Yeah. Do you have a comment or no? No?
Yeah,
Jack?
it's relating to the human aspect of it.
No, I don't want to entertain that. Yes.
So what's a competitive inhibitor?
So we talked about this yesterday, right? No, we didn't talk about this slide at all.
No, we did.
Okay, so just to remind you, a competitive inhibitor is a molecule that binds to the active site of the enzyme, but it can't be broken down by the enzyme. It's just getting in the way so that when the competitive inhibitor is there, the substrate can't get into the active site.
So why does it exist? Just to.
Well, because enzymes have
Oh,
certain
okay.
shapes,
Alright.
and like, let me give you an
So
example.
it's, yeah.
Like some poisonous animals, the reason that they're poisonous is because the molecules that they produce are competitive inhibitors for enzymes in your body. So this toxin or this poison that they expose you to might make certain chemical reactions in your body happen less effectively, and that can cause damage or death to certain tissues. So we do the